So we've discussed spectral types of stars, and we've indicated that the absolute magnitude could be related to the size of the star. Luminosity. The luminosity is the total energy output per time. So it's the power of a star. It's related to the absolute magnitude. The bigger the luminosity, the higher the wattage of the star, the brighter it is. So the luminosity is related to the temperature. The bigger the temperature of the star, the brighter it's going to be. The bigger the size of the star, the brighter it's going to be. So that means all these things are related to each other. Which means if you could somehow figure out, a couple of them, you could figure out the rest. So in other words, if you could figure out the luminosity of a star and you could figure out its temperature, you could figure out the size. So if you could find the absolute magnitude, you can find the luminosity. So there's kind of a little bit of work that has to be done here. So we know there's a relationship between absolute magnitude and luminosity. This is the equation right here. And that is that the absolute magnitude, is related to the luminosity of the star and the luminosity of the sun. So this would be an equation you'd see in an astronomy textbook for finding the absolute magnitude if you know the luminosity. Well, that means if you know a little bit of mathematics, you can work this thing backwards so that if you know the absolute magnitude, because we can find the absolute magnitude if we know the apparent magnitude and the distance. And then we could figure out the absolute magnitude. We know the luminosity of the sun, so hey, it's an algebraic equation. We have one unknown, so we just solve for it. Okay, I'm not going to make you solve for that. This is the solution. And that is that the luminosity is equal to 78 times the luminosity of the sun times 10 raised to the exponent m over 2.5. Okay, now, good news and bad news, mostly good news. You're not going to have to actually use this equation. It's just nice to know that an equation exists that tells you, how all this stuff relates. So we're not just making it up. We already mentioned this, however, way back when we were looking at the idea about light, and that is luminosity is related to the Stefan-Boltzmann law, related to the temperature of the star to the fourth power, related to the area. The area assuming a star is roughly spherical, now they're not really all spherical, but assuming they're roughly spherical, then that'd be 4 pi r squared. And so that means parallax, 1 over p or 1 over pi, depending how you define that, gives you distance. Distance would give you absolute magnitude. Apparent magnitude plus absolute magnitude could help you figure out luminosity. Luminosity, the spectrum or the B minus V, that would give you the temperature. So that plugs in here. We know the size of the star. We can solve for radius. In other words, the radius of a star tells you how big it is. And so we can now figure out how big stars are. And so putting some of this stuff into perspective, our own solar system. Earth is this little tiny thing here. So the small terrestrial planets, you could fit 1,000 Earths inside of Jupiter. You could fit 1,000 Jupiters inside of the sun. The sun dominates our entire solar system. But the sun is comparatively a small star to some of the other stars. Sirius, brightest star in the nighttime sky, is quite a bit larger. Pollux and Arcturus are what you actually call red giant stars, and you could fit like 1,000 suns inside of Arcturus. Well, Arcturus is pretty small, so you could probably fit 1,000 Arcturuses inside of Betelgeuse, and Betelgeuse would fit inside of Antares with room to spare. Now remember, Betelgeuse is so big. If you put Betelgeuse where the sun is, the outer edge of the star would actually swallow up the entire orbit of Jupiter from one side to the other. Jupiter orbits the sun at about 5.2 AU. So that means the star is bigger than 10 AU across. So that's enormous. That means you put the edge of If you put the edge of that star where the sun is, the other edge of it would stick out past the orbit of Saturn. Betelgeuse, fairly nearby star for these red supergiants. It's famous for being the star in the shoulder of Orion. As I said before, stars have all these different names. Betelgeuse is Alpha Orionis. It's also 58 Orionis. It's also got a BD number, an SAO number, a Hipparchus number, HD number, and a Guide Star Catalog number. And that's only a handful of the names that it has. As it rotates, it gets brighter and dimmer, and so you can sort of reconstruct what the surface would look like. And so this gives you an idea as to just how big that star is and kind of what the surface looks like with bright and dark. The actual biggest star in the sky, what would that be? What's the biggest star that we found? We're not exactly sure. It depends on how you define it. Remember, one of the things you have to do is figure out the luminosity and the absolute magnitude, and that's really hard to do if you're just guessing at distance. And some of these really, really bright stars shine so brightly you can see them from really far away, much farther away than you can easily find distance. Our best guess, depending on who you ask, is the star Scuti. And so there it is, drawn in scale to the sun, which is that pixel right there. And so this is an idea, this is our best possible scale that we can make on the screen here. But Scuti is probably one of the biggest stars that's out there, and it's so big you could fit 5 billion suns inside of it. And that's a pretty big star.